Hello, we are team 4 and we're doing the final presentation for project 2. Team 4 is made up of 4 members: Marielena Mora, Maximum Shroma, Abraham Bugdu, and myself, Abraham Vasquez. So for the introduction, in class we've been doing 1D and 2D final analysis elements, but for 3D final elements, problems get more complex, and that's when ANSYS comes in handy because it helps to solve those problems. And then we use SolidWorks to import geometry into ANSYS, so we built a system in SolidWorks and then imported it to ANSYS. We ran final simulations, including assignment materials, generating meshes, and applying boundary conditions and loads. We analyzed deformation, stress, and factor of safety for the system. So the design challenge, we analyzed bolted joints, as you can see here on the picture on the left. So we had 3 different bolts, M16 and M12 and M18, which is 16 millimeters, 12 millimeters, 8 millimeters in diameter. We ran simulations and compared the performance of 3 different bolts. We also use fasteners in the joints to capture and join other parts by securing the components with mating screws. As you can see here on the picture on the right, this is the system that we used for project 2. And the bolts secure the 2 square plates together, as you can see here. And then we ran about 16 simulations with different materials, 9 simulations with aluminum alloy and copper alloy. As you can see here, we use different forces for bolt pretension and tensile load in the simulations. We also had simulations for the combined loadings, which is both the tensile and shear loadings along the bolt pretension that are applied to the system. And then the constraints. So we have 4 constraints. So for this one, it was the bounded contact between the bolt and the nut, as you can see here. And this is the ANSYS once the system was in ANSYS. And then another one was between the 2 plates. We had frictional contact between the 2 plates. As you can see here on the right again, the system of ANSYS, the contact points between the 2 plates. And then frictional contact for the top plate and the bolt head. It also had a coefficient of a frictional coefficient of 0.2 between the two, as you can see here on ANSYS, the 2 contact points. And then frictional contact between the bottom plate and the nut also had a frictional contact point with a coefficient of 0.2, as you can see here on the picture on the right in ANSYS, the 2 points of contact. And yeah, that would be it for me. Thank you.
Hello, my name is Maria Elena, and I will be talking about our ANSYS results for the system, the bolt, as well as the plate for both the aluminum alloy and the copper alloy. For the most part, the pictures, just by looking at it from just a picture perspective, we can see that for most of the systems, they're pretty much identical to one another for the 2 materials. We can see that a lot of the stress is being placed, for example, like the top plates, is more on the outskirts of it, which we can also see for the copper alloy and the aluminum alloy. But one thing I did want to point out is for the bolt, we can see that it is red towards the middle of the bolt, which means that there's a lot of stress being placed there, which is where the 2 plates of the system will meet. And there's also a frictional force being applied there, so there's a lot of focus at that point. So that would be a reason as to why we should pay attention to what material as well as what bolt size we use for the system. Because if we were to use a smaller bolt, for example, like the 8, having all that pressure placed at that point with such a small diameter of a bolt will break the system and therefore make the system like unable to use, or it's deformed at that point. So being able to have a good bolt size is very important. And the way we determined which of the aluminum alloy and the copper alloy were good enough was by looking at the factor of safety. The higher value that we see in the factor of safety will determine which one is better. And by looking at our ANSYS results, we can see that the aluminum alloy was our best option in this case for the combined loading of the actual system. And we want a high number of factor of safety to make sure that the system is able to hold its shape under this type of condition that we placed on it, which was for the bolt retention and the tensile load. We did, like I previously mentioned, choose the M12 bolt for the aluminum just because it gave us the higher factor of safety. But I also did want to touch on the fact that we could also have gotten better results for the factor of safety, possibly a higher, or I would say a more correct value if our square mesh for our system was better. As we can tell from the picture on the right, we can see that on the edges of the actual system, the squares were pretty much the exact same size, but as we come to the top of it where the bolt is, we can see that they're starting to disfigure and therefore causing our results to be not as well done as they could have been if we had placed the mesh differently. So that could also have changed our values that we got from ANSYS. So just kind of like for a future reference, maybe we could look at changing the mesh that we place on our system in order to get better results if we were to push this further. Thank you.
Hello, this is Maxim Srama, and I'm going to do a conclusion and wrap up any questions/concerns that we still have. Our bold choice was M12 because it is a perfect balance between strength and safety, so it makes it an optimal choice for multiple applications. For example, an increase of factor of safety of something as minimal as zero point 0.2 is not worth any additional costs. For our material selection, we decided that aluminum is preferred in applications where a low weight and a high strength are necessary, such as in the aerospace field, especially where cost is a huge factor. Copper, on the other hand, has overall better tensile and yield strength as seen from our results, and is also used in applications requiring good ductility and moderate strength. Our overall strategy, according to our results, under multiple loading conditions, we aimed for a medium-sized bolt since it is a balanced approach to stress distribution and safety. Answering our first question on mesh optimization, choosing the optimal mesh size for simulations involves a balance between accuracy and computational efficiency. While for our project, Mesh 5 was perfect since it didn't take much time, other projects might take hours or days with that mesh size. On safety margins, safety factors can range from 2 to 6, depending on the potential risk involved in the unpredictability of operational loads. For example, in aerospace, factors of safety are often lower due to a need to minimize weight. Safety factors might range from 1.2 to 1.6 for different parts of the aircraft. And on accuracy, efforts to continuously refine simulations through better modeling techniques, more precise data, and validation practices help ensure that simulation conditions closely mirror real life environments, which provide insights to product performance and safety. Thank you.
Hello, my name is Abraham Budo, and I will talk about how ANSYS has transformed our engineering projects. This slide talks about the capabilities of ANSYS software. ANSYS enables effective simulations and analysis of various engineering systems, linking these simulations to real-world scenarios. It provides insights into how factors like both size, material, and loads impact system. This deeper understanding aids in enhanced structural integrity and resilience, leading to optimized designs. This slide discusses the benefits of mastering ANSYS. By integrating this software into our processes, we've deepened our understanding of complex systems. Mastery of ANSYS helps us apply theoretical knowledge, sharpen our judgment on simulation results, and make informed strategic design choices. Overall, it improves project resilience and helps us manage the balance between design feasibility and structural integrity. This slide highlights how ANSYS has enabled us to address various challenges, improve collaboration, and boost efficiency. It shows how adaptability and overcoming software limitation and unexpected issues. The slide also emphasizes the importance of validation, assumption in engineering when complete data isn't available, and underscores the necessity for continuous improvement and critical evaluation in our work. Thank you so much for your attention, and this concludes our Project 2 final presentation. Thank you.